So first of all, I would like to thank all of you for being at this awesome BSides, really a community-driven event, and it's really my pleasure to be here. I know all of you guys are busy, so I'll try to make the most of the next hour that I have here. So let's get started. While registering today for this event and when I got this badge, I was talking with a couple of folks about their expectation from BSides, and not just from BSides but from my talk. Some folks were really excited to hear that there would be like packet sniffs and Wireshark dumps in the presentation, while some folks said, well, we could do that more in the privacy of their offices, their cubes, their garages, and they really want to focus more on what's happening in the bigger picture on the industry and what are some of the trends and so on and so forth. So what I'll try to do is keep sort of a balance between both of these so that both the audience are, if you may, entertained a bit. So my name is Amol and I work for Qualys in the Vulnerability Management Group. This SCADA thing started for me about 5 years ago, when one day all of a sudden my boss comes to my cube and says, hey, do we have signatures to identify SCADA vulnerabilities? So to give you a little bit of a background, what my team does is we write signatures that identify vulnerabilities, misconfigurations, possible threats, any sort of loophole by which an hacker or an attacker could get into your network, could compromise your network, and so on and so forth. And remember, this was 5 years ago. I knew what SCADA was a little bit at the time, but was in no position to start writing vulnerability signatures for those. So I said, well, okay, we don't know exactly what SCADA is at this point, but we'll start investigating for the final thing, which is to write signatures for those. So as I started talking with a lot of people in the industry, started attending various SCADA conferences, what hit me was that what I refer to as SCADA may not be, or may be entirely different than what someone else refers to as SCADA. Some people, and there are a lot of differences. Some people say, okay, this is not SCADA system, this is really an industrial control system, this is really a distributed control system, so on and so forth, and there are differences. But for the purpose of this presentation, I would sort of use the word SCADA loosely and interchangeably for all these systems. So I said, fine, let's start investigating. If I may ask you a question, what are some of the pictures that come to your mind when I say SCADA? And these were some of the pictures that came to my mind at that time when the word SCADA was said. Electrical power lines, pipelines carrying either water, natural gas, petroleum, so on and so forth. And these are all examples of SCADA systems. The sort of rule of thumb that I have is, if you sort of hug a system and if you end up hugging a country or half of a continent, then yeah, that's most probably a SCADA system, and the top 3 systems are kind of the examples of those. The systems on the bottom are more or less referred to as industrial control systems, where they are big, they are huge, but they are still somewhat confined to a plant, a big plant or a set of plants. So for example, food industry, donut manufacturing, automobile industry, car manufacturing, so on and so forth. So I was wondering, why was this interest in SCADA? I started investigating, and there have been some accidents in the SCADA space. The links that I have here, they are pointing to some of the root cause analysis done by the US government on some of the liquid pipeline failures, some of the power failures, and other accidents. And again, at the end of this presentation, I'll point you to a link where you can find this, so you don't have to write down anything. So I said, fine, okay, there have been accidents, but that was not pressing reason enough to start writing vulnerability signatures for SCADA systems. So I started looking into more. There have been cases of vandalism, and the example that I have here is from Portland. Some of the vandals, they destroyed some of the rubber gaskets on electrical poles. Didn't cause an outage or anything, but still the electrical company had to send down crew, replace the gaskets, reroute power, and did cause them a little bit of a headache, a lot of money to do that. So fine, there have been cases of vandalism which may justify writing vulnerability signatures and scanning for those. There had been insider threats, and the example that I have here is from a disgruntled employee. This is an example from Australia where an employee was fired from a water treatment plant, a sewage plant, and the very next day what he does is, because of his knowledge of the system, he goes in and opens up the sewage system into rivers and parks. So I said, okay, that's something pretty serious, and that is one of the reasons that one would try to secure their SCADA systems. But what I failed to notice at that time was the threats, or the advanced persistent threats that we are seeing today. These are threats from states to other states or from terrorist groups. And the link that I have here is for the Duku worm, which has been said to be a son of Stuxnet. And the folks at Symantec here think that people who created Stuxnet also created Duku. It doesn't really do anything for now, it just goes and finds information, but these are some of the things that we could see in the future. So I said, okay, fine, there have been credible threats for securing those. How do I go about understanding the system, writing signatures for these? What we usually do when we have such a task is we get the database, the device, or any system in concern in our labs. We bang on it till it breaks, we find vulnerabilities, and then we write signatures. Or if there are known vulnerabilities, we write signatures for those. But if you recall all the pictures that I showed you, it was, well, impossible to get all those systems in our lab to start sort of pen testing them or banging on them to find vulnerabilities. So what we did so that our engineers could understand these SCADA systems in a much better way was created a sort of a framework that could be applied to, well, almost any industrial control system or SCADA systems, and then they can be studied. So this is what we came up with. What you see there on the left hand side is the field. So these are the components that would be maybe thousands of miles away in the field, and on the right hand side is your control center where you would control this system. So if we take a more detailed look at what it looks like, is on the left hand side are data acquisition components. So these are components like sensors, meters, field devices. And what they essentially do is convert parameters, like for example here I have a photosensor which converts light into an analog signals, or temperature or pressure into analog signals. These components maybe would be mounted on, for example, a gas pipeline or on electrical poles or whatever, wherever you need to sense those attributes. This data acquisition component had sort of a two-way communication with the next component in our system, is the data conversion component. This component basically consists of PLCs, IEDs, or RTUs, programmable logic controllers, intelligent electronic devices, remote terminal units, and they convert your analog or discrete measures to digital information. And the examples starting from left to right, what I have is a PLC, IED, and RTU. And to give you how big these components are physically, I have another picture of a man with a PLC in his hand. So okay, what we have on the left hand side is I/O, sensors, meters, which acquire these characteristics. Then we have this data conversion components. And then this converted data is passed to the SCADA master using one of the many SCADA communication protocols. Now this communication could be over radio, over Ethernet, over various channels, and using any of the SCADA protocols that some of the examples of which I have mentioned here. They say that there are hundreds of SCADA protocols, proprietary, non-proprietary, open source, closed source. I haven't been able to count up to 100, but there are really a lot of SCADA protocols out there, and we'll see in subsequent slides a little bit more in depth about these protocols. So fine, data is acquired, it's converted. Using one of the communication means, it gets to this presentation and control layer, which is essentially where a human being or an operator continuously monitor alarms and acts on it. What you see on the left hand side is a pretty traditional control center where you have certain monitors or human machine interfaces where you see what's happening in the plant, and the operator basically monitors. Usually there are 24/7 operators monitoring these alarms and reacting on those. On the right hand side, what you see is a little bit more modern HMI. Actually, these diagrams are from the HMI designers, but a lot of modern HMI systems do look like the ones on the right. So this is sort of a framework that we came up with to classify these systems, so that we essentially ourselves could understand these SCADA and industrial control systems. So we said, fine, okay, this is what sort of most of them look like. Where are the threats? So threats could be at the I/O and remote level, so between your sensors and PLCs. But a lot of these threats require physical access. So a threat could be that you go and change a sensor or a meter or tamper with them in the field. So the example of vandalism that we saw could be categorized here, where someone just goes and destroys something, which requires physical access. But field equipment generally does not contain process knowledge. So if you as an attacker just go there without having any background about the system, about how it works, and just remove something, vandalize something, you generally would not know what would be the effect of this, because field information is something like valve 16 or breaker 9B. Unless you have a full picture, you don't know what that does. And without process knowledge, this leads to basically nuisance disruption, like the vandalism example that we saw. So we said, okay, there are some good, credible threats here, but at least at that time, and even today, I don't think, or at least in my knowledge, there have not been too many threats of this sorts. So we said, okay, let's try to focus our attention more on communication. Threats in communication basically imply you manipulate FEP directly, and which would change the HMI output. So what comes from this side, you change that, so the operator there at the HMI station gets to see something different than what is really happening in the field. And there were a lot of protocols, a lot of SCADA protocols. So we said, okay, this is something that typically as computer science engineers, as signature writers, we have been more accustomed to is protocols. So we decided to take an in-depth look in some of the SCADA protocols. We looked at Modbus, which is a pretty old style protocol, a pretty old protocol, but nevertheless used in a lot of control systems. It's a very simple client-server protocol, and all of you would have no problem in basically writing anything for Modbus. If you know Telnet, if you know FTP, if you know any client-server protocol, it's not exactly, but it's sort of the same. What you have is you have a Modbus client, a Modbus server. There is a request that comes from the Modbus client, goes to the Modbus server, and then there is a response that comes back. The only difference that you have is the Modbus client is the master, while the Modbus server is the slave. So that's a little bit different than what we have in our typical TCPIP sort of protocols. So Modbus was not really designed initially to run on TCPIP, and but it was later ported to TCPIP. So Modbus consists of its ADU or application data unit and PDU, which is the program data unit. And the way it started running over time on TCPIP was just by putting the entire protocol inside your TCP and IP header. So now I think it becomes more clear for all folks here who are very well versed with TCP/IP. Is you just put the Modbus packet inside your TCP packet, which is inside your IP packet, and just send it over. So let's take a little bit detailed look, removing all the TCP/IP thing from the Modbus protocol. What you have is a Modbus header which has a transaction ID, protocol ID, length, and unit ID. So transaction ID is basically very simple. It's a transaction. So for example, if there is a photo sensor there and I'm asking the photo sensor, hey, how is the light there? Or if there is a temperature sensor there, what is the temperature? I say this is or basically the client says that this is transaction ID 100. Give me the answer. What is the temperature right now? And then the response that I get is for the transaction ID 100, by which I know that, oh, I had requested temperature for transaction ID 100, and this is the response. So it's a simple transaction ID. Protocol ID is fixed for Modbus. Length is basically the length of your packet, and there is a 1 byte unit ID. Now this is, let me go back a little bit for this. So what you have is you have a PLC, and there could be one or more PLCs or one or more sensors connected to that PLC. So when I request a temperature there, by specifying a unit ID, I specify that, okay, this is the unit that I want the temperature for or pressure for. That is specified in the unit ID. So which destination PLCs or sensors am I querying for? So pretty simple so far. If you look at function codes, they are also pretty simple. They are function codes like read discrete input, write discrete input. I want to read maybe input or I want to read temperature for these certain coils, or I want to read temperature or pressure or whatever that is connected to, for 10 of them, for hundreds of them. And there is a opcode associated with every request. So pretty simple here as well. And data finally is the data as per the opcode which is in the function header. So pretty clear so far. Everyone with me? Yeah. Okay, I see a few heads nodding. So, well, if you can easily write a Perl client to create a Modbus request. As we saw, you have a transaction ID here. I've put it as 256. Protocol ID is always 0 for Modbus. You basically create the length for the entire packet. You put the unit ID, which I have put as 1 here. You put all the data as per your function code, which is, I have specified 3 here, which is basically read a lot of data. You create a socket and you send away your request. Pretty simple. If you copy paste this example in Perl and run it against a Modbus device, it will send a Modbus request. And the response that, so yeah, and when you send that request, you will see something like this in your Wireshark dump. Now Wireshark and almost all sniffers already have very good support for Modbus. We didn't have to write any packet decoders for these, and we were sort of fortunate in that request, in that sense. And what you see here is your transaction ID, your protocol identifier 0, your length, your unit identifier, and what you want to do is I want to read multiple registers, and I want to read 5 registers. So let's say if that PLC was connected to a temperature sensor, I want to read like 5 temperature readings. And the response that you would get from such a request, in this case, what I received was, okay, this was the transaction ID that I had sent, and it copied the same transaction ID in its response. Length was 13, and it gave me a byte count of 10. So I asked for 5 temperature readings, and it gave me 5 temperature readings, 2 bytes each. So I got 10 bytes back. Again, pretty simple. I think everyone is following with me till here. But the main question that we have to ask using this simple example of a Modbus client-server communication is that what does Modbus provide? This is a sort of a triangle that every protocol or every security protocol is measured against: availability, confidentiality, integrity. By availability, it's usually authentication and authorization. Authentication is basically, are you are you really who you claim who you are? And authorization is, are you really authorized to do the action that you are asking me to do? And we saw in the previous example that the code didn't really have or didn't really provide any authentication or authorization in it. It just said that, okay, give me this reading. It didn't have to say who I am. It didn't have to say I am authorized to do this because of so and so. It just said, give me this reading, and you got a response saying, okay, these are the readings. So pretty much there is no confidentiality here. There is, again, pretty much no integrity here. I could be a man in the middle, change anything in the middle, and instead of a write request, I could change it to a different type of write request or a different type of read request, and I would get the results back. So pretty much there is no confidentiality or integrity. So we said, okay, this itself is a vulnerability. So what do? We try to find Modbus installations at our at our customer's network, put that in our signatures, and sort of notify them that, hey, you are running Modbus, which is fine, but make sure that all your other security measures are there around this protocol, since inherently this protocol is not secure. And again, I'm not here to bash Modbus or something. It's an excellent protocol. It just was not designed for security. So we said, okay, let's take a little bit of a more recent protocol, and we chose DNP3, which was designed sort of from the ground up for the electrical system, and try to see how DNP3 works. So DNP3 and Modbus fundamentally are the same, which is basically you ask for certain readings, it gives you a certain readings, you write to it, or you sort of change certain settings, and those settings are changed. So fundamentally it's the same. It has, although, a lot of differences with Modbus. Differences like DNP3 has strong data types which Modbus doesn't have, or Modbus is strictly polling. So you have to always constantly poll. Give me the temperature, give me the temperature, give me the pressure. You always have to poll. But in DNP3 you have the ability to say that, okay, give me the temperature only if it changes. So it reduces network traffic. Also, there is timestamping. So in Modbus, as you saw, there was no timestamp. So the client sends the request and receives a response. Now the client has to assume that, okay, I sent a request at this time, and so the response that I got must be for the request at that time. But meanwhile, the temperature or pressure could have changed. So that was not really acceptable for the electrical system. So there is a concept of timestamping there, that you say, okay, this is the timestamp on my request, and when you get data, you get a timestamp saying that, okay, this was the parameter at this timestamp. So it's a little modern protocol than Modbus. So SCADA SAN. So before going a little bit into DNP3, this is the output of the pull request and of the open source tool that we are updating today. And what it can do is it can scan your network or scan other people's network for the presence of Modbus protocols where Modbus servers are present, and can sort of brute force the Modbus IDs. And I'll go into more detail about this little tool or utility that we are releasing in a bit. So coming back to DNP3, as I mentioned, it's a layered protocol. It has a link layer, a pseudo transport layer, and application layer. It's a little complicated than Modbus, and we won't go into a lot of details into DNP3, but take just a quick overview. So this is the DNP3 application layer headers. As you could see, it has similar sort of thing which has request headers, response headers. The request headers are basically read, write, select. So logically it's doing the same thing as Modbus is getting parameters, getting from the sensors. This is the transport layer header, and it sort of tries to provide the same functionality as the TCP transport layer. Not quite, but similar. And this is the link layer where you have the start of the packet, which is always this 0x0564, the length of the packet, control bits, source address, destination address, CRC. Well, now we have CRC, and various different function codes. So what we did was, okay, let's create another Perl example of a DNP3 link layer frame and send it away. So this is exactly as we saw in the header. Is we created a packet with the start byte, with the length, with control, with source, destination, the CRC, and well, created a simple TCPIP socket and send it over. The request looks something like this on the wire. You can see all, and again, even in this case, most of the packet sniffers are pretty good at DNP3, and we didn't have to write any custom plugins for Wireshark or Ethereal. So we were really lucky in this case. You see the request that it's sent basically, which is a request for a link status. I'm trying to find what is the status of the link, and with various parameters, and I got a response from DNP3 saying that, okay, these are the status bits of the link, and well, 1 is basically on and 0 is basically off. So I sent a request, I received a response. Same question again that we asked with Modbus. What does DNP3 provide? Did it provide confidentiality, authentication, authorization? Not really. Integrity, maybe a little bit, because it had some CRC, but again, not really any confidentiality. So we created again signatures to identify DNP3 protocol and say that, okay, if you are using this protocol, then be careful, make sure all your other security measures are in place if you are using this protocol. But well, okay. So, and this is an example of the open source tool again that we are releasing, running in the -T or in the DNP3 mode. More of which I'll come back later again. But all is not lost in these two protocols. Soon in 2007, the DNP3, the next version of the DNP3 was released, which had a lot of good things, including hashing, including key management functions, including a lot of good things that are needed to basically satisfy this pyramid. So if you are using DNP3 in your installation, make sure if you have the secure version or the 2007 implementation of DNP3 and it's configured to use these different new security features that have been added. So we looked at a lot of communication threads and protocols, and the common theme that we had was basically a lot of these protocols were not designed really to run under TCPIP. Now they do run under TCPIP, but they have been not really designed with security in mind. So you have to have a lot of other controls present if you are using these protocols. Coming to SCADA masters, as I said, threads on SCADA master, these are the places where this is a place where all the control happens. So usually what happens is when you walk into a SCADA master room, you have some sort of a good authentication mechanism to go inside the room, physical access. There are, as I showed you in a couple of pictures ago, a lot of flat screens or some screens that give you status and operators continuously monitoring these alarms and basically ready to act on them. The number one thread that we saw for SCADA masters was that the control system network or this SCADA master network was inadvertently connected to your corporate network or sometimes even to the internet. Now, it used to be that these networks were completely different from your corporate network. So when you go in to work every day, you go log in, you check your email, you do your certain task, and that network was completely different than the SCADA master. And on paper, in many organizations, yes, this network is different than your SCADA master network. But what we found was that inadvertently, your SCADA network was connected to your corporate network, or in some cases even to internet. When Stuxnet was a pretty hot thing, I'm not sure if you have heard of a website called Shodan. How many of you have heard of Shodan? So yeah, a couple of hands. What it does is it's a crawler. It basically scans all the websites, all the servers on the net, and stores their IP addresses and their banners. So if it is a FTP server, it will store its banner. If it's a HTTP server, it will store its banner. If it's a telnet server, it will store its banner. So after Stuxnet, and it had search, and it shows what were the top searches. So after Stuxnet was released, the top searches there were for PLCs, were for the vulnerable PLCs that Stuxnet targeted. So I went in, I put my little search for, let's say, GE or some ABB or various manufacturers for SCADA systems. And even when you go outside this presentation, you can go to Shodan and try to find if there are any control systems on the internet accessible to you. And as of yesterday, I was still able to find some systems that gave that were on the internet. So that's the number one, I think, problem with with the SCADA master systems. Secondly, there is no authentication or poor user authentication. So as I mentioned, usually the SCADA master is a room, a physical room, and it has when you go in, there could be like a fingerprint scanner or maybe a guard there to make sure that unauthorized people cannot get in. But once you get in, this is let's say this is a SCADA master terminal. I can just go and tinker in with anything. There is no real authentication for that terminal, and that was fine when your master network was totally segregated from your corporate network. But now, since that's not the case, all the viruses and worms, they don't really need to physically go in the room and do anything. They can just hop on from your corporate network into the SCADA master, and if there is no authentication on, let's say, the HMI software application, they can directly manipulate these applications to give, let's say, wrong instructions to the PLCs, to give wrong instructions to do something, or maybe to retrieve data from these PLCs. And again, if there is no authentication, there are very few systems with poor user authentication. So as to log what operator did what. There are shared passwords or default passwords, and in one of the conferences that I attended with Joe, and by the way, there are two really SCADA experts here with us today. So if you want to join, if you want to talk with them, feel free and talk with me or talk with Joe and here, who have really dedicated their entire life in control system security and in just control system. So in one of the conferences that I went to, the number one reason given for not having passwords on the HMI system was that because an operator has to respond to an emergency, it's an alarm, maybe something is burning, something has exploded, something is leaking. There is no time for that operator to key in a long password and then know what the alarm is or to react to it. But at the same conference, there was a military, there was some guy from the U.S. Navy. I don't know. Do you remember, Joe, who that was? Both Air Force and Navy, and they said that, well, we have 25 or 18-year-old cadets typing in 25 character passwords which are changed every 2 weeks, and they have no problem in doing that. Now in the military you could do that, but I think it's time that we start thinking about these control systems as really systems that are important for our critical infrastructure, because they are critical infrastructure systems and they are very critical. No patching. So this was also something that has been discussed in the control system areas, that often these systems are not patched, and there are various reasons around it for not being patched. It's not just that the control system operators are lazy or something, that they do not want to patch, but it's that around 2000, or maybe in the 1990s, in the late 90s, when Windows started to become the predominant or the most or a pretty famous operating system, a lot of control system owners asked their vendors to port a lot of their software on Windows because it was cheaper. Instead of having a proprietary system from end to end, if you could sort of migrate some of the HMI components on Windows and have the operator log in there, have the graphics there, it's much more cost effective. But what happened was the entire patching concept of Windows came to control systems. So now when Microsoft releases a patch, how many times a month? I'm pretty sure everyone knows, once every patch Tuesday. You have to patch this critical control system, which is not possible many times. On top of that, control system vendors, not all the time, there is no real guidance from these control system vendors on what would happen if you apply a patch. So let's say I'm owner of a control system. I have a system from some vendor, and my vendor doesn't tell me if I apply this Microsoft patch, what would happen to this system. I would be really scared to apply that patch, because this is the control system which operates maybe some really important temperature or a dam or I don't know, something and important, and I don't want to apply a patch for which I don't know what would happen if I apply that patch. So there is no patching guidance from control system vendors, or things have changed a little bit, but for the most part there is not much guidance from the control system vendors. So lack of patching is definitely an issue for control systems. Not restarted in vendors. So we saw systems that were running Windows 2000, Windows NT, and they have not been even restarted in many years. There were a lot of precautions been taken, like UPS and a lot of other things around those systems so that the system doesn't go down. And when asked, why have you not restarted the system, the simple answer was that, well, we are not sure if the system will come up again. So if you are in that state where you are not really sure if the system will come up again if you restart it, then I think you are really in deep trouble. As a lot of systems are migrated to standard Windows or Solaris systems, the same issues that apply to these Windows or Solaris systems or any off-the-shelf operating systems, like unnecessary services, hardening of the operating systems, and so on and so forth, they apply now to control systems as well. So some of the challenges that we saw, and the most daunting challenge, is the long life cycle of a SCADA system. These systems are meant to last for decades or multiple decades, 30 years, 40 years, 50 years. They're not like your laptops which you can replace or which are replaced every 3 to 4 years. And the challenge is in upgrading partially some of the components in the systems. And the long life cycle of SCADA systems, I think, is a challenge that we could overcome. And I'm going to talk about that in a bit. There is no testing or guidance from operating system vendor patches. Some systems are directly managed by SCADA vendors. So although you own the system, you do not have administrative level privileges on that system. So we went into an instance where it was a Windows system. We were asked to sort of scan it, and we said, oh, we have seen lots of Windows system, easily done. But then when asked for credentials, they didn't have admin level credentials, which were with the vendor who provides that system. So the owner couldn't really do a good assessment of that system if there are unauthorized services or not, because they really don't manage these systems. Other things, like on the SCADA master network, there are a lot of other systems like data historians, which are basically databases, off-the-shelf databases, Oracle, MySQL, so on and so forth, which also needs patching and which are also affected by the same vulnerabilities that as other off-the-shelf software. And in more than one instance, we saw a lot of internal differences between the securities team and the team which really managed its SCADA networks. And because of these differences or differences of opinion, what ended up happening was there was no real scanning or auditing that happened. One of the instances was that, well, someone from the IT just ran blindly a scan of the SCADA system, and a lot of PLCs and RTUs, they just were knocked off because it was like a standard SYN scan that you would run against operating systems, and that caused a lot of havoc. And then they said, okay, no scanning, no auditing, we'll deal with it later. So if you are someone in the IT organization who is responsible for the security of the SCADA system, make sure that you scan them with certain settings that are suitable for scanning these systems. So some of the proposals that I have is you could have some sort of password policy, access control roles on these SCADA systems, have some strategy for software upgrades and patching. As the software that you are getting gets older and older, it becomes difficult and more difficult to upgrade and patch. So, SCADA test environment, this is easier said than done. If your SCADA system costs like $1 million, then it will almost cost you half to have a working test environment, and that's why there are no test environments, at least in the instances that we have seen. But you could have simulators and SCADA software or vendors giving a really small test systems that you could test for patching and so on and so forth. You could demand from SCADA vendors to expedite on operating system patches, give you guidance on what will happen if you apply the patch. And basically, since a lot of SCADA networks are now starting to look as your normal IT networks with Windows and Oracle and so on and so forth, try applying your usual IT network management security skills to the SCADA network as well, which would take you a long way. So finally, SCADA Scan, this is an open source tool that we are releasing an update. We are releasing an updated version today. What it does today is it scans your network for Modbus slaves, for NP3 slaves. It is really an alpha version. In the beta version, we are adding support for SCADA master vulnerability scanning, vulnerabilities for HMI and so on and so forth, SNMP support. And in the 1.0 version, finally, what we want user configurable signatures. So we have not seen all the SCADA systems. There are various different types of SCADA systems. So what we want is the owners of these systems, if possible, to run this tool and upload the signatures. If this tool has never seen a system like that, upload that signature to this open source tool so that others can really benefit from this community effort. We are not there yet. We are at the alpha version today, but we'll get there. And I'll have updates on my Twitter feed about where the tool is and what sort of updates we are having it on a day-to-day basis. So that's the location of where the tool is today. That's my Twitter handle. If you're interested in updates on the tool and generally updates on various other security vulnerabilities that come on a day-to-day basis. I'm almost out of time. I think maybe we have time for 1 or 2 questions. Go ahead, Joe.
Might be interested in. It's called Protecting Industrial Control Systems from Electronic Threats. And it's there so people can understand what the differences are between control systems and IT systems. There's been more than 200 actual control system cyber incidents to date. In the US alone, 4 have killed people. We've already had 3 major cyber-related electric outages. We've had 2 nuclear plants shut down from full power. We've had a water pumped from a Superfund site into the drinking water system. Those are just some of the things that have already happened. You don't have to try and figure out what might be. I happen to be the managing director of ISA 99, which is the International Society of Automation. 99 is process control security standards. One of the working groups is 9906, and I would encourage anybody here to join. That's patch management for industrial control systems. And the reason is that you may use Windows on a control system, but it isn't Windows. It's Honeywell Windows, or it's ABB Windows, or it's Emerson Windows. If you take a standard Microsoft patch and apply it against these systems, you will crash the system. Not maybe. So one of the things I would heartily suggest, if you want, go to isa.org. Go to ISA 99, but 9906 is patch management. The other thing I wanted to point out, actually a couple real quick ones. The biggest issues with control systems are that we've got systems that have design issues with security. They are not patchable, they are not fixable. That is what Stuxnet went after. You cannot patch the vulnerability that went after because it is part of the design of the controller. And we have a number of controllers with those types of issues. So there's two things going on. One is what Amol is talking about. Make sure that the, if you will, network security part is taken care of. The other is the actual control system piece. And what you've got to have is a team of people like me or others who know the control systems, as well as the security people who know the network and security piece, because you won't get there from here without it. The last point I wanted to make out is, or point out, is that one of the reasons you don't restart systems is because bad things happen when you restart systems, especially if a facility is operating. We just had a case, literally 2 months ago, where 2 units were operating and somebody restarted a system that hadn't been restarted. It shut down the logic in every single one of the processors in the distributed control system. If you can imagine, 214 processors all lost logic with a plant operating. Never did we think that was possible, and it happened. Total loss of control, loss of view, loss of everything with a plant operating.
Thank you, Joe. So I think we are out of time, but feel free to talk with me and to Joe and to everyone here who are from the control systems and have any of your questions answered. Thank you.